So we are looking at chapter 11. You guys got it. This, I think, is going to be the beginning of life getting easier. So I think that this is a fairly easy chapter. So that's nice. So this chapter is about the complex numbers. So if you remember back from your Algebra 3-4 class, the complex numbers, we denote that set with that special C. And it's the set of things in the form A plus BI, where A and B are real numbers, and I is the imaginary number that's equal to -1. Right, so this is just our definition for the set of complex numbers. So for example, 3 minus 2i is a complex number. 10 is a complex number. -6i is a complex number. Thanks, dude. Trevor, it's for you. No, you just have to pick something up at the office. It's not a big deal. You're not in trouble.
You never get notes.
Well, it's just something to pick up. So what it boils down to here is basically everything classified still as a complex number, right? Whether it was a real number before, or a purely imaginary number, or one of these that are kind of like an imaginary part and a real part. They're all complex numbers. That's what it boils down to. Our question here becomes, if we think back to real numbers and we have 3/5 and 0.615 and the square root of 2/2, and we ask you to put these things on the number line, you could do that, right? We draw a number line, and 0.6 is here, there's 3/5. What does what mean? This is the member of the set. Right? We've used that notation like when we've done domains and ranges and all that. It just means a member of a set.
The one after that?
That's the symbol we're using to define the complex numbers.
Okay.
If that's 0.6 and this is 0.7, then 0.165 would go here, and square root of 2/2 is 707, so it'd go over there. Right? And we can rank these things from biggest to small, so we can put them in order. We can line them up on a number line. That's one of the properties of the real numbers, is that they're ordered. They're ordinal numbers. You can put them in, you can sort them in order. Everybody okay with that idea? What if we wanted to do the same thing with complex numbers? Let's say we have 3 plus 2i, and then 2 plus 4i, and then 5 plus I. Which one should come first on a number line? No. Right? It doesn't work. So one of the features of the complex numbers, if you talk about all complex numbers, is they're not ordinal. You can't put them in order from biggest to smallest. You can't line them up on a number line. Although we'd like to still have some graphical representation of them, because the complex numbers have two parts. It has, they have this real part and an imaginary part. We're going to need a two-dimensional number line to represent them. We call that two-dimensional line the complex plane. Oops, plane, not pane. So we'll just kind of draw a two-dimensional axis. The The vertical axis we call the imaginary axis, and the horizontal one we call the real axis. So if I wanted to plot 3 plus 2i, that's 3 plus 2i. If I wanted to do 2 plus 4i, that's 2 plus 4i, etc. Everybody's okay with that idea? Now, what does this remind us of? Hopefully it reminds us also, not only just graphing a point, but vectors. Right? We have, to get to that complex number, we have, like an x component, a y component, and then a distance from the origin. Right? We'll revisit that in a moment, mostly because what it allows us to do is it allows us to add two of these complex numbers together. So if I take a complex number, we'll call that one Z1. And we'll say I have another complex number. Let's say that one is Z2. And I want to find Z1 plus Z2. So what I'll do is I'll kind of do this the same way that we would for a vector. So I'll draw like another imaginary axis there, and I'll plot like Z2 relative to that. So it's like boom to boom. So this is like my same thing that we did when we added vectors, right? What it boils down to, though, is if Z1 is like A plus BI, and Z2 is C plus DI, Z1 plus Z2 is just add the real parts together and add the imaginary parts together. The same way when we added vectors, right? We just add the x component, we add the y component, and we're done. Everybody's okay with that? Okay. So that's adding vectors. Pretty easy, right? Another property for vectors that we had is we're interested in the magnitude of the vector, how long it is, right? So the equivalent of absolute value, remember in Algebra 1, you would have defined the absolute value as like the distance of a number to 0 on the number line. If we talk about absolute value for complex numbers, we're talking about the distance of that number to the origin of the complex plane. So if I have some complex number z here, this distance is like the absolute value of z. We call this, though, the modulus, is like the more general term for this absolute value thing, because the modulus can apply to, we can use, if you want to get very technical, modulus can be applied to a number system like in any dimension. So like in a one-dimensional system, the modulus is just the absolute value. In a two-dimensional number system, the modulus is the distance to the origin. In a three-dimensional system, it's different, in four-dimensional, five-dimensional, etc. We're not going to go past two-dimensional because the real number, or the complex numbers are in a two-dimensional plane. It's a two-dimensional number system. But basically, all this boils down to is if I take the modulus, or the absolute value of a complex number, it's just going to be the same as the magnitude for a vector, right? Still the same formula. We take the x component squared plus the y component squared, and we square root them. Still doing the same thing, right? Do we see that? Okay. If I wanted to define this angle, we can say the same thing that we would for vectors, and we could say that angle is equal to, tangent of that angle is equal to b over a. So again, we could define a complex number equivalently by describing its magnitude and its direction, like we would in the polar coordinate system or like we did for vectors. This allows us to give an alternative definition or a trigonometric form for a complex number. So if I have the complex number a plus bi, that is equivalent to the trigonometric form where a is going to be is r cosine theta, and b is equivalent to r sine theta. So we can just say that this is, actually let's do that. Let me move it here. So I can say then that's the same thing as saying z equals r cosine theta plus r sine theta times I. So let's do an example of that transformation. So let's say that I have the complex number -2 plus 5i. Okay with that? Just some complex number. And I want to rewrite it in that trigonometric form. So I would take a moment and quick sketch a little picture. So there's my complex number that I've gone 5 up and 2 to the left. So this is my value for r, is that side length. And there's my value of theta that I'm going to be searching for. So far, so good? Okay. R is the same thing as the absolute value, or the modulus, of this complex number. So that's just going to be 2 squared plus 5 squared, square rooted. So that's the square root of 29. Everybody happy there? And then theta I can't find directly, but I know that theta is going to be 180 minus this alpha. And alpha is going to be tangent inverse of the absolute value of y over x. When I type that into my calculator, that is about 68.20 degrees. So theta is about 111.8 degrees. So I can say my trigonometric representation is the square root of 29 times cosine of 111.8 degrees plus I sine 111.8 degrees. Or you could put the square root 29s as coefficients to both of the trig functions. That's fine too. Sometimes it's tricky with the I. Where do you put the I? I did it that way. But whatever. You could distribute the square root 29 through if you wanted. No big deal. But this should feel pretty easy, right? It's just like what we did for vectors, just like what we did for polar coordinate system. You're seeing a lot of repeated ideas here over and over and over again, right? What do you suppose is the reason for that? Well, one of the things that we never talk about in high school mathematics class is that there's like a broader overall structure to algebra. So there's like these broad overall algebraic structures. And it happens that the complex numbers and vectors and like the polar coordinate system are all kind of this same algebraic structure called a vector space, or maybe a module if you're being a little bit more general. But they all have the same algebraic structure. So it turns out that like things with the same algebraic structure are all kind of the same. Like the labels are different and maybe some of the details are different, but everything works kind of the same way. And that's what's going on here. And it's really fascinating that you have like this big overarching like governing body. And one of the things you'd be particularly interested in as an algebraist is finding these different overall structures, because what you can do is if you can prove something that's true for one of these structures, you can find the analog in any one of these other things that is an equivalent structure. Which is cool, right? You can find an analogous theorem kind of in all these different places. And it allows you to do things that are maybe really difficult one way. If I just think about it instead as this kind of a space, then, oh, I can do this and this and this and this, and then transform it back to what I had before, and it's a lot easier. Anyways, that's like beyond the scope of this course, but since it keeps happening to us, we keep seeing things work the exact same way as they have before, I figured it was worth mentioning. We're going to talk about now multiplying and dividing. So if we are in the standard form, I just have like a plus bi times c plus di, what do you suppose you'd want to do here? FOIL, right? Do exactly what it looks like. So you get ac plus ADI plus BCI plus BDI squared. And remember that I squared is equal to what? Is it -1? Good. So I have then AC minus BD, that's like my real term, plus AD plus BCI, that's like my imaginary term. Basically, we can just FOIL stuff out, right? If they're in the trigonometric form, so let's say we have R1 times cosine theta 1 plus I times sine theta 1 times R2 times cosine theta 2 plus I times sine theta 2. So let's say we're doing the same thing in trigonometric form. So I can multiply the R1 and R2 together, and then I can just FOIL the parts in parentheses, right? So cosine theta 1 times cosine theta 2 plus I cosine theta 1 sine theta 2 plus I cosine, or sorry, let's do the theta 1s first. Sine theta 1 cosine theta 2 plus I squared sine theta 1 times sine theta 2. Get that all on the screen in one place.
So you make the A and the C and the H and the D into cosines?
So remember how we just said there was like two ways to represent a complex number? So I'm just doing the same thing with the trigonometric representation. That's what this one is. So I'm just doing the same thing because we're going to create a shortcut here to do the multiplication in this representation. Because as you might be thinking, it's like, why the heck do we need two representations for the same thing? Like, why do I need two ways to represent a complex number? What we're going to find here real quick is that the trigonometric representation makes multiplication division really easy. We just need to develop the shortcut, which is what we're doing right now. Okay? Okay. So what I'm going to do then is, again, we recognize that I squared is -1. And I'm going to group this term and this term together. And then I'm going to group this term and this term together. And you might say, why are you grouping those things together? Well, the reason is that hopefully, after I point it out to you, you recognize this formula. That formula is cosine theta 1 plus theta 2. And hopefully recognize this formula, which is sine theta 1 plus sine theta 2. Whoa! Oops. Oh, yeah, that's fine. So, everybody okay with that? So just as a couple of quick examples, let's say that we have 3 plus 2i times 5 minus 4i. This one we're just going to FOIL. And we're done. Everybody's okay there? Here, let's say we have in trigonometric form So here I have two complex numbers in trigonometric form. So according to my last formula, I multiply the two coefficients together, so 5 times 2. And then I add the angles, so 36 plus 14 is 50. And I'm done. That's pretty rad. I used the formula that I developed in the previous.
So we don't need to do any of that.
Right.
Oh,
Because the formula here just says if I multiply two complex numbers in trigonometric forms, I multiply the coefficients and I add the angles and I write it in trigonometric form, which is pretty rad, right? Talk about a time saver. Whoop-de-dee-whoop. Okay. So division. So again, let's look at something in our standard trigonometric, or our standard form for a complex number. Again, from last year in your Algebra 3-4 class, you remember to divide two complex numbers. What we're going to do is multiply by the conjugate. So then we FOIL. So that's going to be 15 minus 21i minus 10i plus 14i squared over 25 plus 7. The conjugate's the same thing with the different sign in the middle, is the simple way of saying it. So when I combine like terms here, I'm going to get, 1 minus 31i over 32, or really we write that 1 over 32 minus 31 over 32i. Is that okay? You guys kind of remember doing that last year? And that's kind of a hassle, right? What? You can sit in front of Teresa or something if you need to, see a little better. Okay. What if we did this in trigonometric form? So let's say we have this. Now I could do the same thing I did on the previous one, but I'm going to skip the derivation and just go straight to the result. Because it's okay, of course, that's how it's going to work out. So if I take the two complex numbers in trigonometric form, I divide the coefficients and subtract the angles, where the angle on the numerator is subtracted by the angle in the denominator.
Theta 1 minus theta.
Yep. Which is pretty rad, right? It's basically the same formula as the multiplication, except instead of adding the angles, you're subtracting the angles. Instead of multiplying the coefficients, you're dividing the coefficients.
How do you know this?
Well, I skipped doing the derivation. I'm just writing this down as a formula. Because if we compare this to the multiplication, it's like the exact same thing, except they're minuses instead of pluses, and it's division instead of multiplication. But we did do the same, basically the same derivation as we did before, but it's twice as long because now I'm foiling both the numerator and denominator, so it's kind of a hassle, and I just didn't want to do it. But it basically boils down to the denominator turns into a 1 when you multiply by the conjugate. And the numerator is the same thing you had before, but now there's a minus in between them instead of, like every other term is negative instead of positive. So you regroup, and instead of being sums, they're subtractions.
So since the R1 is 4 over R2, you just take the cosine.
Yeah, so let's do an example, like an actual numeric example here to kind of cement things. So let's say we have the square root of 12 times cosine of 19 plus I sine 19 divided by square root 3 times cosine of 12 plus I sine 12. So this is just going to be 2 cosine plus I sine. Done. So square root 12 divided by square root 3 is square root 4, which is just 2. And 19 minus 12 is 7.
So how can you so for the conjugate, you're taking that bottom and then just multiplying it.
I'm not multiplying by the conjugate here.
Oh, okay.
I'm just using this formula that we wrote down above.
Right.
Now, the way we got that formula was multiplying by the conjugate, yes.
Right.
But we're skipping doing all that work because we're developing this formula. Is that okay?
Yeah, I just didn't know how you were getting like so.
Okay. But that's, again, just using the formula basically, right? All right. Here's my favorite thing in the whole chapter. So powers and roots of complex numbers. It's not so bad. The key is using the trigonometric form. Okay? So if we have, say, a complex number squared, z is just a complex number. That's the same thing as z times z, right? So that's going to be, if we do the trigonometric form, like r times cosine theta plus I sine theta times r cosine theta plus I sine theta. If I apply my formula, I'm going to get r times r and then cosine of theta plus theta, and then I sine theta plus theta, or 2 theta. Everybody okay there? Now if I did z to the third, that's the same thing as z times z squared. So I'm just going to have r times cosine theta plus I sine theta times my previous result, which was r squared cosine 2 theta plus I sine 2 theta. So if I do it again, I have r times r squared, r cubed, theta plus 2 theta, so cosine 3 theta, and sine 3 theta. Do you guys see a pattern going on here? So that pattern is z to the n is r to the n cosine n theta plus I sine n theta. Which is pretty rad, right? Because think about what you'd have to be doing without the trigonometric form. If I had like 1 over square root 2 plus 1 over square root 2i to the 10th, it's a lot of foiling, right? Now I guess you could use the binomial theorem if you really wanted to, but that's still pretty annoying. It's a lot of combinations to compute. Just as an aside, let's kind of examine geometrically what's happening. So let's say that this is z, and this angle here is theta, and this length is r. Okay? Z squared is here, where this length is r squared, and that distance is 2 theta. Right? And then if we did it again, there's z cubed, where this length is r cubed, and this distance is like 3 theta. Everybody okay with that idea? Okay. Let's just note that this is just equal to itself. 1 over square root 2 plus 1 over square root 2i to the 8th. It's just equal to itself. Who's impressed? How did you do that so quickly, Mr. Kulik? This point I recognize as a 45-degree angle, right? With radius 1 because it's a point on the unit circle. 45 times 8 is 360, and I'm right back to where I started again. Because the length of the vector is 1, so when I every time I square it, the length doesn't change. It just ticks around the unit circle, and I'm back to where I started again. Whoa! This is a special algebraic structure in itself. This is an example of a cyclic group, where every member in the group, every member in the set is just the power of some other member in the group, and there's finitely many powers. So in this case, there's just 8 unique elements in the group, or in the set, I should say. There's 1 over square root of 2, and there's like 0, 1, and there's negative 1 square root of 2 square root of 2, and then negative 1, 0, and then negative 1 square root of 2, or negative 1 square root over 2, 0, negative 1, and there's just those 8 things in the set, and any power of any of them is just some other member of the set. You just have to around the unit circle enough times to kind of connect this back to what we did in first semester, which is pretty cool. Is everybody okay with this idea? Ostensibly, you can just use the formula that we developed, but I wanted to give you like some geometric intuition of like why this is working and what this is actually doing, connecting it back to the unit circle and things that we've done before, and because it's pretty neat. Or not. Maybe it's really like, oh my God, I'm so overwhelmed right now.
I love that.
I do too. I think it's really exciting. All right. Square roots. You remember that a square root is equivalent to the exponent 1 over 2, right? Everybody agree with that? Now I'm just going to use the previous theorem because 1 over 2 is an exponent, is it not? So that's just going to be r over 2 cosine theta over 2 plus I sine theta over 2. But that's not quite right. Why not? Well, let's think back to this example here. So if I have 1 over square root of 2 plus 1 over square root of 2i, and I take the square root of that, so here's 45 degrees, and our point, our value is e. So when I take the square root of it, it's going to get half as long, and the angle is going to be half as big, right? But that's assuming this is our angle theta over 2. What if this was our angle theta over 2? Still describing the same number, isn't it? Or what if that was our angle theta over 2? Still describing the same location, is it not? So what do we need to do to our formula here? We're just going to add everything coterminal to it. Oops. Let's actually say just that. Now let's go ahead and just generalize this all the way. So we are talking specifically about square roots here. So if we wanted to do this for an nth root, nth root of r. Oh my goodness. Did I write this over 2? I'm so stupid. That's supposed to be square root of r. My goodness gracious, Mr. Kulik. What a dummy that move was. Well, excuse me, Mr. Critical. Is that better? All right. Yeah, no problem. Okay. So let's do some examples of taking some roots now. Okay? So let's say we want to find the cube roots of 3 minus 2i. So the first thing that I would do, I notice that my complex number is not written in trigonometric form. I'm going to convert it to trigonometric form because life is so much easier when it's in that form. So r is the square root of 3 squared plus 2 squared. It's the square root of 13. And if I plot this, so 3, negative 2 is down here. This is our angle theta. This is our angle alpha. So I know theta is going to equal 360 minus alpha, where alpha is the tan inverse of the absolute value of y over x. So when I type this into my calculator, (360 minus tan inverse of 2/3), 326.31. So far, so good? Okay. So when I take the cube root of that, it's going to be the cube root of the square root of 13 times cosine of 326.31 plus 360k divided by 3 plus I sine 326.31 plus 360k divided by 3 for k equals 0, 1, 2. Since the n in this case was 3. So 2 is n minus 1. Everybody so far so good? Okay, so now I'm going to plug this stuff into my calculator. So I have also worth noting that this is the same thing as just the 6th root of 13. Do you guys remember doing that in your Algebra 3-4 class? No? So let's show you why we get that. Remember, square root of 13 is 13 to the 1/2. A cube root is to the 1/3. Exponent of an exponent we multiply. So I get to the 1/6, which is the same as my cube root 13, or sorry, 6th root 13. So for k equals 0, I have the 6th root of 13 times 326.31 over 3 plus I sine 326.31 over 3. So I'll go to my calculator. Cosine 326.31 divided by 3 times 13 to the 1/6 is negative 0.493. And I do the same thing for sine, and that's 1.452. So k equals 1. I'll do the same thing, but this time I'm going to do the 6th root of cosine 326.31 plus 360 over 2 plus over 3 I sine 326.31 plus 360 over 3. What are you okay there? So that's 686.31. So that's going to, when I type that one in, I get negative 1.011. And I do the same thing for sine, and I get negative 1.153. Everybody okay there? And I have one more to go. That's when k is equal to 2. So again, cube root 13 times cosine 326.31 plus 720 over 3 plus I sine 326.31 plus 720 over 3. And go to the calculator and type those bad mama jammas in. So plus 720 is going to be 1046.31. So that gives me 1.504. And I do the same thing for sine, and I get negative 0.299. Oops, forgot the i's on these. These aren't points, dummy. We're not writing these as a vector. We're writing these in complex number form. Sorry. So I should probably nix the parentheses so they don't look like points. That's it. Guess what we did today? We did the whole chapter. In less than an hour, guys. That was a full chapter in less than an hour. No.
Test next month. Test next Tuesday.